Have you ever thought of math as, well, as a machine? Something that takes in a number, does one simple thing to it, and then spits out a brand new number? Well, that's pretty much what a function is. Today, we're going to dive into these little mathematical machines and see how algebra gives us the perfect language to write down their rules and, just as importantly, keep them nice and tidy. So, here's our game plan. We'll start with this idea of a function machine, then figure out how to draw a picture of what it's doing. After that, we'll bring in algebra to write the rules, and finally, we'll learn the super useful skill of cleaning up our algebraic expressions. Let's get right into it. All right, first up, the magic function machine. This is such a simple idea, but honestly, it is the key to really getting what a function is and what it's for. The most important word there is relationship, but it's a very specific kind. A function is a consistent rule. It's predictable. You put a number in, and you are guaranteed to get one specific number out every single time. No surprises. It's really just a simple three-step process. Step 1, you feed it an input, like the number 4. Step 2, the machine does its thing, it applies its rule, in this case, add 3. And step 3, out comes your output. And with this machine, if you put in a 4, you will always get a 7. Okay, so talking about this is one thing, but seeing it, that can make everything click. We can actually draw a kind of map that shows exactly what our function machine is up to. A table is a fantastic way to keep track of all this. Let's say our machine's rule is multiply by 2. You can see the pattern instantly. Put in a 1, you get a 2. Put in a 3, you get a 6. Each input has one and only one possible output. Super clear, right? And this is what we call a mapping diagram. It's called that because we're literally drawing an arrow that maps each input directly to its one and only output. It's just another really clean visual way to see that function doing its job. So far, we've been using specific numbers, which is great. But here's the thing. What if we want to write down a rule that works for any number we can possibly think of? This, my friends, is where algebra becomes our superpower. And that's the big question, isn't it? Instead of making a gigantic table that goes on forever, how do we just capture the rule itself in a short, powerful way? This is exactly the problem algebra was born to solve. And the solution is so simple and so smart. A variable. We just use a letter, you'll see X a lot, to act as a placeholder. It's basically a little box that says, hey, you can put any number you want right here. So check this out. If we just call our input x, our rule add 4 to any number becomes this tiny little expression, x plus 4. And that's it. That little phrase holds the entire rule. It works if x is 10, if x is 1,000, or if x is negative 1,000,000. It just works. Okay, so now that we can write these expressions, you'll find they can sometimes get a bit, well, long and messy. But just like tidying up a room, algebra has a system for organizing everything. We call it simplifying. The secret to tidying up in algebra is to think of it like you're sorting groceries. You've got apples and you've got bananas. You can put all the apples in one pile and count them, and all the bananas in another, but you can't just mash them together. In algebra, we do the exact same thing with our variables. So here's the deal. Like terms are basically terms from the same family. They have the exact same variable part. So 3a and 4a are like terms because they're both a terms. They're both apples. But 3a and 3b, those are unlike terms, an apple and a banana. You can combine the first pair, but you absolutely cannot combine the second. All right, enough talk. Let's actually do this. We're going to take a messy-looking expression and use this whole like terms idea to make it simple, clean, and much easier to work with. Okay, here's our starting expression. We've got 4 different pieces here and 2 different variables floating around, p and q. Our mission is to combine whatever we can. First things first, you've got to spot the families. Find the terms that belong together. Using colors, like we've done here, makes it super obvious. You can see the p terms, 4p and 2p, are one family, and the q terms, 3q and negative q, are the other. Now we just do a little shuffling. We're not changing any of the math, not at all. We're just reordering things so that all the family members are sitting right next to each other. It just makes the next step really, really clear. And here's the payoff. We just do the simple math inside each group. 4 p's plus 2 p's gives us 6 p's. 3 q's minus 1 q leaves us with 2 q's. Our final simplified answer is 6p plus 2q. And we stop there because P's and Q's are different families. We can't simplify it anymore. Oh, and here's a quick but really important tip. It's kind of like grammar for algebra. The number, which we call the coefficient, always goes before the letter. So we always write 3x, never x3. It's just how it's done. So let's do a super quick recap. A function, it's just a consistent rule connecting an input to an output. A variable, like x, that's our tool for writing a rule that works for any number. And simplifying expressions? It's just about tidying up by grouping together all the terms that are from the same family. And this is really just scratching the surface. I mean, think about it. Calculating your monthly phone bill based on data usage, figuring out the total cost of your groceries, these are all real-world rules that you can now write down and simplify using the exact tools we just covered. So the real question is, what will you describe first?